Okay, our last gas law relates to what's called Avogadro's principle, named after Amadeo Avogadro, the person for whom the mole is named after, 6.02 times 10 to the 23rd, Avogadro's number. Now, Avogadro's principle says this, that equal volumes of gases at the same temperature, pressure, contain the same number of particles, regardless of what gas we're talking about here. So, if we had temperature and pressure that is at STP, then we would have exactly 1 mole of gas in the container if the container contained 22.4 liters, like that. Now, if we were to graph the relationship, number of moles increases, volume increases. That's provided that temperature and pressure doesn't stay the same. Now, how would this look? We have the combined gas law, which is PV over T is some kind of a constant. And then we have N, which is going to represent the number of moles or number of particles in a gas. If we put that into the equation, we would put it into the denominator. And then we would end up with some kind of a constant, P times V divided by N divided by T. Now, this constant actually has some special meaning for us. If the pressure, volume, and temperature conditions were STP, then the volume would be 22.4 liters for 1 mole, and the pressure 101.3 and 273 Kelvin. Multiplying these all together, we end up with this, and it have the units of kPa times liters divided by moles divided by Kelvin. This constant is known as the ideal gas constant, and it's quite useful for us then to do calculations. All right, we have then what's called the ideal gas law. All right, for changing conditions, we have PV over N over T equals PV over N over T, P1 and V1 and P2 and V2 sort of thing. Now, that's for changing conditions when we have 2 pressures, 2 volumes, or 2 temperatures and number of moles. Now, for absolute conditions, that is, if we wanted to relate pressure, volume, temperature, and number of moles together, we have the ideal gas law that looks like this. P times V equals N times R times T. And what is that R? R is the ideal gas constant. And the units of it depends upon what units we're using to measure pressure, volume, and temperature. For this, we would need to, if we did measure our pressure in kilopascal and liters, volume in liters, and N in moles, of course, and then T temperature in Kelvin, then this would be our ideal gas constant. If we had different units, then we would have a different number for the ideal gas constant. Here are some different variations for the ideal gas constant. The first one is if we are using liters, kPa, moles, and Kelvin for our units, then we would use 8.31. If we were using liters, milliliters, mercury, and Kelvin, we would have 62.4. If we were using liters and atmospheres, moles, and Kelvin, then we would have 0.0831. All right, and there are other ones too as well, based on if we use, say, for example, PSI or torr or some other pressure unit as well. All right, we of course always want to have our temperature in Kelvin. And of course, N is the number of moles. So depending upon what unit for the volume and what unit for the pressure we use would determine what value of R we use. Now, most of the time, we would try to keep our pressure in kPa, our volume in liters, and then of course moles in Kelvin for and then for T. And then we would use 8.31 for the ideal gas constant. Okay, let's look at some sample problems. All right, now, if we have a question such as, what volume would 2.5 moles of gas occupy at 104.5 kPa, and T at 25 degrees. Now, the first thing we got to do is get that temperature to be in Kelvin, which means we would have to add 273. So that's going to give us 298 for our temperature in Kelvin. All right. Now, N is the moles, 2.5. P is the pressure in kPa, so we're going to use 8.31. And then we want to have our volume, probably would be measured in liters. Now, remember, R is a constant, always given. In this case, 8.31, and then that would be measured in kPa, liters, divided by moles, divided by Kelvin. All right. So if we want to solve for V, we have to take PV equals nRT, ideal gas law, solve for V. V then would be equal to nRT divided by P. And that would then give us 2.5 times R, which is 8.31, times T, which is 298, divided by P, which is 104.5 kPa, and the calculator says 59.2, and that would be in liters. All right, let's try one more. How many moles of gas are in 2 liters at? So 2 liters, that's going to be our volume, 2 liters. Temperature is 24 degrees Celsius. That needs to be in Kelvin. So 296 Kelvin. Pressure is in atmospheres, and remember that 1 atmosphere is equivalent to 101.3 kPa. Well, let's convert it into that so we can use 8.31. And then R is our ideal gas constant, 8.31 kPa times liters divided by moles divided by Kelvin. All right, we are then left to solve for N. Now, using the ideal gas law, PV equals nRT, solving for N would be then equal to PV divided by RT. So our pressure is 101.3. Our volume is 2 liters. R will be 8.31. And T is 296. Calculator will say 0.082. 0.082. Then solve for N, that is moles. We'll label it as moles. All right, let's try one more problem. For this last problem, I think we'll skip this because we won't have this kind of problem on the test.